Hello IB, welcome to chapter 23, section C on expectation. So we're going a bit further with our probability this time. In this case, we're looking at if we have an experiment happening and we've done n trials and the probability of getting a particular result is p, then the approximate number of times this event will occur is n times p. We would have done this a lot in the middle school years. So n times p, and for example here, if we're tossing a die 90 times, how many 2s can we expect to get? So the number of 2s, is simply going to be, it's a funny looking 2, 90, because there are 90 trials. What's the probability of getting 2 on a normal die is 1/6. So we would expect 6 into 90 is 15. So we would expect to get a 2 15 times. Does that mean we'll get it 15 times? No, it doesn't. This is like an average result. So if I toss the dice 90 times, I might get 17. And if you tossed it 90 times, you might get 16, and somebody else might get 14. But on average, we would expect it happening 15 times. So someone might get 15 times, but not necessarily. And that's the thing about probability. It's what we would expect, but it doesn't always say what happens. What about if we want to come up with a general result, but we're doing more than just like tossing a coin and how many 2s? This is called an expected outcome, or the mean result. And we give this the symbol mu, that sort of Greek letter. It looks like a U with a bit of a tail on it. So mu is the expected result when we have a whole lot of different possibilities. So in other words, if we had, say, 1,000 people doing that same experiment once, what would their average result be? So if they all just tossed a coin, tossed a die once, what would be the average number that they would receive or get when they tossed it? What we then do is add up all those little multiplications we just did on the first board, where we get the result times its probability. So getting a 2 times 1/6, or 3 times 1/6, and we add those all up to come up with our average result. So x is the result, or the value of what the outcome of the experiment. Let's go outcome. And p is, of course, is our probability. And we do that for all the different outcomes, probability, and add them all up. So if we go back and look at our fellow lady, whoever's selling magazines at the shop, and we have different numbers of magazines being purchased by different people. And we talked about the random variable being the number of magazines that were purchased. So this is our random variable x. And we get the different outcomes, buying 1, buying 2, buying 3, 4, 5. This is the probability that they happened, just based on statistics. There's your graph. So in other words, on average, how many magazines would you expect someone to buy? And it doesn't mean they're going to buy that number, but what's the average result? So if we want to get the average result, we just simply want to go the expected outcome, E. X is like what we're going to get, is to get 1 magazine, the probability of that happening was 0.23. Then we're going to keep adding, because that's what our sigma notation means. So that sigma notation means add these all up for all the possibilities. So we're going to have now 2 times 0.38. And the chance of someone buying 3 was 0.21. The chance of buying 4 of them was 0.13, and the chance of buying 5 of them was 0.05. If you put that in your calculator, you'll come out with a result, which is, I wrote it down here, 2.39. All right, so that's the result of adding that all up. So what does that mean? That means that on average, a customer will buy 2.39 magazines. So on average, a customer will purchase or buy 2.39 magazines. It also means if we had 100 customers, then we could expect to sell 239 magazines. So it's good having that sort of statistics for planning. So that's what that average result means. Let's now look at another example where we use this is in gambling. So games involving gambling, a game is considered fair if the expected gain is 0. So if the net result is 0, then we say that was a fair game. So let's go back to our example of throwing a die. Let's say, for example, we said, well, if you throw a 1, you're going to win $8. What's the probability of that happening? 1 in 6, assuming it's a fair die. If you throw a 2, you're going to win a 7. Again, the probability here is 1/6. If you throw a 3, you're going to get nothing. 1 on 6. If you throw a 4, you're going to win $6. So 1 on 6. If you throw a 5, you'll win $4. This is looking really good. But if you throw a 6, you're going to lose $2. So now we do the same thing. We're going to multiply our outcomes. So this is like our X's, the amount of winnings we're getting. This is our probability. So what's the overall expected return, the overall gain from this? We're going to go 8 times 1/6 plus 7 times 1/6, 0 times 1/6, etc. And obviously for the ones where we're losing, we're going to now make it plus -2 times 1/6. So that comes out with this equation here. All right, so don't forget to, I just include that even though it becomes 0, but it just helps you check you've got everything in there. Then when we go down and evaluate all that, that can simplify down. Our net result then is $3.85. 83 at least. What does that mean? It means on average you're going to win $3.83. So this is like our average result. All right, so that means if I had, say, 1,000 people and they all threw the dice, that would be the average gain. But you could throw the dice and get a 1 and get $8. Or you could have thrown a 3 and got nothing, or I could have thrown it and got a 6 and had to pay $2. But on average, that's the result we get. But most games, you're going to have to pay to join in. So what would be the expected gain if the player has to pay $5 to play the game? So when we do that, we do our same sort of calculation with the 1/6 times 8, etc. through to, what are we doing, 1/6 times -2. But now, because we have to pay $5, we now subtract 5. So instead of winning $3.83, we also, the average result of winning $3.83, we're going to subtract the 5, and means the net result is a loss of $1, What are we up to? 17. So overall, you will end up losing. And again, if we go back here, you could have paid $5 to play the game, thrown a 1, and you are ahead $3. Here, if you threw a 2, you'd be ahead $2. Here, you may have paid $5 to play the game, thrown a 6, and then you've got to pay another 2. Overall, you've got a loss of $7. But this is an average result. Would you play the game? No, you might say, well, I'm feeling lucky. But I probably wouldn't, knowing you're going to lose that all the time. Quick bit of research. In New South Wales, there is what's called an RTP, a legal return, RTP. That stands for return to player. In New South Wales, it is 85%, which means any club, casino, hotel where they're playing pokies or anything like that, the machines are set to return only 85%. You can guarantee, on average, you will lose 15%. So, on average, over the long term, you will lose 15%. That doesn't stop you playing the first game and winning a whole lot of money. At that point, walk away, because in the long run, that's what will happen. Sorry, I'm quite against gambling because it's people lose, and anyway, the clubs are there to make money and they're making it out of you, and if you're happy to do that, fine. Anyway, let's look at this last one here. Here's our random variable. We need to calculate the expected the average or the mean for this distribution. Here's our formula. So if x is equal to 1, 2, or 3, what's our probability? So the probability when x is 1 will be 1 squared plus 1 makes 2 out of 20, which equals 1 out of 10. Our expected probability for when x is 2, how about you pause the video, fill this in and calculate mu, and we'll come back and see where you're at. Okay, so hopefully you've got that, multiplying the probability by the score and come out with 2.5. So the average result is 2.5, which you can see is very different than just taking the average of 1 plus 2 plus 3. So hopefully you've got a few good notes from there, and we'll see you in class. Thanks for listening and have a nice evening.